Have you ever been staring at a textbook and this symbol pops up? The upside-down triangle, squared, and you just feel your brain start to shut down a little? Trust me, you are not alone. This is the Laplacian operator, and yeah, it looks like some seriously abstract math, but it actually describes something incredibly physical, something you can feel. In this explainer, we're going to pull back the curtain and give you a rock-solid intuition for what this thing really means. For so many of us in engineering and physics, the Laplacian, delta squared, it's just one more operator in a whole sea of vector calculus. It feels like a roadblock, right? Something you just have to memorize for the test and then hope to forget. But what if it's way, way more than that? Okay, here's the big secret, the main takeaway. That's exactly what it does. The Laplacian is basically a mathematical tool that measures how much a value at one specific point differs from the average of all the points right next to it. You can think of it as a measure of lumpiness. And by the end of this, you'll be able to see that lumpiness just by looking at the math. So, how do we get from a scary symbol to something intuitive like lumpiness? Well, the trick is to stop thinking of the Laplacian as one brand new scary operation. It's actually a two-step process using two ideas you might already know, the gradient and the divergence. Okay, so here's the formal definition. The Laplacian of a scalar field V is the divergence of the gradient of V. I know, that sounds like a mouthful, but all del square V is a shorthand. It's a compact way of saying, first take the gradient of V, and then take the divergence of whatever you get from that. Let's just break that down. Step 1, you take the gradient of your scalar field. Now remember, the gradient just gives you a vector field, where all the little arrows point in the direction of the steepest climb, like arrows showing you the fastest way up a hill. Step 2, you take the divergence of that new vector field you just made. And the divergence, that just tells you if those arrows are spreading out from a point or converging into it. All right, this is where it all comes together. To make this whole thing concrete, we're going to use the best analogy there is for the Laplacian, a simple, stretched rubber sheet. So just imagine our scalar field is this sheet. The value of the field at any given spot is simply the height of the sheet at that spot. So high points on the sheet mean high values, low points mean low values. Simple enough, right? Now check this out. Pick a point right at the bottom of a dip, a little valley. That point's height is obviously lower than the average height of all the points immediately surrounding it. It's kind of like a sink. This situation, where a point is less than its neighbor's average, that corresponds to a negative Laplacian. And as you've probably guessed, the opposite is true. A point at the very top of a peak is higher than the average height of its neighbors. It's a source. And this perfectly illustrates a positive Laplacian. It's literally just a measure of how much that one point pokes out from its local neighborhood. So what about a point on a perfectly flat section, or on a perfectly smooth, even slope, like the side of a ramp? Well, the value at that point is exactly the average of its neighbors. There's no peak, there's no dip, the curvature is 0, and in this special case, the Laplacian is 0. This special state is called a harmonic field. Definitely keep that word in mind. Okay. That rubber sheet is a fantastic analogy in 2 dimensions. It gives us the core intuition. But of course, in engineering and physics, we usually have to work in 3 dimensions. So how do we take this idea of lumpiness and turn it into a mathematical tool we can actually use for our calculations? Whoa, okay, don't be intimidated by these formulas. I know they look like a lot. Just think of them as different tools in a toolbox. If your problem is shaped like a box, you use the Cartesian formula. If it's shaped like a can or a sphere, you pick the right tool for that job. They all calculate the exact same physical property, that lumpiness we saw on the rubber sheet. Now, let's go back to that really special case where the Laplacian is 0. This isn't just some mathematical curiosity. Nope. It is the absolute foundation for one of the most important equations in all of electrostatics. And here it is. Welcome to Laplace's equation. It's so simple, it's beautiful. It just states that the Laplacian of some scalar field V is equal to 0. And going back to our rubber sheet, this equation describes any region of that sheet that is perfectly smooth. No local bumps, no local dips. The value at every single point is perfectly balanced by its neighbors. And so, there's that word again. When a field satisfies Laplace's equation, we say that field is harmonic. It just means it's in a state of perfect equilibrium, or perfect smoothness. So why does this matter so much? Well, because so many things in nature are always trying to find this kind of balance. Laplace's equation is absolutely fundamental for describing electric potential in areas without any charge, for understanding how heat flows, for modeling how fluids move. It really is a cornerstone of physics.
Okay, before we wrap up, I have to mention one really common and super important gotcha that trips up a ton of students. We have to be crystal clear about what kind of field we're applying this operator to.
Everything we have talked about today, the divergence of the gradient, the rubber sheet, all of it, that applies to the Laplacian of a scalar field. The result is just a number, a scalar. But there's also something called a vector Laplacian, which acts on a vector field. And as you can see, it has a completely different definition and a totally different physical meaning. It is not the divergence of the gradient. Confusing these two is a classic mistake.
So let's recap the three most important things to take away from all this. Number one, the Laplacian of a scalar is just the divergence of the gradient. That's it. Number two, its physical meaning is all about curvature, or lumpiness, how a point compares to its neighbors. And number three, when that curvature is zero, we get Laplacian's equation, which just describes a perfectly smooth, harmonic field.
So the next time you see that delta square symbol, I want you to see something different. Don't see scary math. See a physical question being asked. Is this point part of a peak, a valley, or a smooth surface? It kind of makes you wonder, doesn't it? What other profound physical truths are just hiding inside the symbols we use every single day?